right. So thanks everybody for coming to this meeting. We're really excited. We have two great presentations for you today. And I will introduce the first speaker, Andrew Roberts. He's a scientist at the Theoretical Division of Los Alamos National Lab. He focuses on simulating polar climate and Earth system models. And he's an investigator in the E3SM project as well as interface projects. And I personally have been a friend of Andrew's for a long time, and I love his talks. I always learn something, so I'm excited to present or to hear this presentation from Andrew. Take it away.
Thank you, Jackie. So just let me know if you can't hear me. I'll try and hold the microphone in a place that's hopefully very clear. So today I'm talking about emerging strategies for fully coupled seasonal to decadal sea ice prediction. This talk is unashamedly focused on work inside the Department of Energy. We are currently in a rapid pivot towards what's called S2, S2D simulation and prediction. And a core part of that work is in E3SM, the Energy Exascale Earth System Model. And another project that I work closely with is Interface, or I'm part of this project, which has been up till now focused on coastal model development and analysis for the Arctic. So this work is really the culmination of research by a lot of people. And so I in no way claim to be the sole owner of any of these ideas or thoughts. There's a very strong collaboration across DOE and many different projects. So I really need to acknowledge all of these people here, and there's a lot of them. And I will be sharing work from some of them in figures you're about to see. So with that note, this is what I'm going to talk about, is an emerging strategy for polar prediction inside the Department of Energy, and how this will potentially influence science elsewhere and hopefully positively influence science elsewhere. And then I'd like to share some work on the current state of the cryosphere and the Energy Exascale Earth System Model in support of these new developments we're looking at. And one thing that we have identified with the current state is that we need to make some critical enhancements to E3SM for S2, S2D prediction. And I'll talk about where we're going with this very rapidly right now towards very high resolution model and a lot of use of artificial intelligence. On that note, I'm going to introduce a new experiment that is only a few weeks old called Blue Pulse, which has been a rapid pivot in E3SM to produce large ensembles for S2, S2D analysis. And then I'm going to talk finally about AI-enhanced E3SM polar development of targets for that. So I will say that this field is moving so rapidly right across the United States right now that this talk was up to date as of 6 p.m. last night. I can't guarantee that it's now current. On that note, the emerging strategies for polar prediction in E3SM have been identified of these three core things. First of all, subseasonal to seasonal to decadal. And one of the reasons for this is not because of a change of US administration. This was being considered before there was a change in administration, and that most stakeholders of interest in the work we do are really focused on at subseasonal, what's happening this year, what's going to happen in the next 10 years, and less so what's going to happen 30 years from now. And so previous Earth system modeling had been focused on much longer timescales, but that's not really what our stakeholders were asking questions about. And so a key part of being in the Department of Energy is that we are interested in energy. And so there's a very large amount of energy produced in the US marine environment, and a very large amount of energy consumed in marine energy transport and consumption. And on top of that, the Arctic is projected to carry about 5% of global shipping traffic by 2050. So these are the core motivations for the work we do, and they're different for other US agencies, but this is what we're focused on. So a key part of what we're looking at here is a simulation regime of accurate coupled initialization and very large ensembles. And that's very different from longer term simulations that we've previously been focused on in E3SM. And for those simulations, we've identified that a really important part of it is that the ocean and the ice hold the most system memory. And so it's important that we get the initial conditions right that are consistent with our coupled model and as close to observations as they can be. And it's also important that that's the focus of being able to produce accurate atmospheric predictions as well. So our initialization of the ocean and ice is also not so focused on the deep ocean anymore, because that's a longer time scale process. So we're really focused on the near surface measurements. And we're now at a point in polar regions where there's a lot of data available at the near surface from altimetric satellites and other satellites that really didn't exist 15, 20 years ago. And so we need to adjust the way we think about poles. Although they are data sparse in the deep interior of polar oceans and in ice sheets, that's not true of the surface. And so we can think about this problem afresh, especially when we're coming in from a different side that we haven't been previously doing data assimilation. We are trying to think about this differently. So with thinking about it differently, artificial intelligence offers these new tools to address data sparsity and have large ensembles. So something we've been always focused on in E3SM is a push towards high resolution. And this used to be called very high resolution, but this is our new definition of what we're calling high resolution. So this is our target for the next 3 years, is the new standard. What we call our standard model will be 12 kilometers globally, 10 kilometers in the ocean and ice globally, and 3 kilometers in land. And our high resolution model is convection resolving. It's not quite convection resolving at 3 kilometers, but it's getting close, and 2 to 18 kilometers in the land and ocean. So the 2 part is what we're aiming for in polar oceans, and we don't need to go quite as high in resolution in tropical areas. So previously in E3SM, many people may be aware that we use unstructured meshes. I'm sharing a composite mesh down here, and those unstructured meshes are capable of resolving certain areas of the globe. So we've found that that has limitations in that it's very, very hard to make a model fully scale aware so that the parameterizations that work at, say, 20 kilometers in an ocean somewhere or 30 kilometers are the same as 1 kilometer elsewhere. And we've identified that as being almost an unattainable target. And it's better that we focus our model development on a specified global resolution range and make sure our model works in that range. And that's part of a move away from using regional enhancement. The reason we can do that is largely because of artificial intelligence. And so the focus here is that we run a really high resolution, fully coupled model, but we don't need to run that very often on a supercomputer to produce ensemble members anymore. Instead, we can use that model to train an emulator and then use that emulator at much lower computational cost to generate very large ensembles. And when I say very large, we're talking of hundreds of ensemble members. So we get a much better probability in predictions. So as part of our shift to AI, we're looking for the intelligent generation of initial conditions. So using AI rather than just data assimilation to relate model physics to observations. And when we're looking at observations, we're specifically looking at satellites that offer key physical insights, like that tell you more than just the surface area of sea ice, but tell you about the volumes and hence something about the energetics of the system. We're also focusing on hybrid AI. So that's where we incorporate physical processes that previously we just couldn't do because they were too computationally expensive. So wave propagation, river deltas, sea ice ridging, and especially for the Arctic, higher order ocean mixing, which has continued to be an Achilles heel of simulating the Arctic. In addition to that, there's tools already being deployed for parameter calibration. So we've engaged in that over the last decade or more for the sea ice modeling at Los Alamos, and that's now being employed across fully coupled models. And AI is also just ramping up right across the infrastructure of our model. And I'm going to share some results today that were 70% generated with generative AI, all the coding behind it. So this is the current state of the cryosphere in E3SM. We have had great improvements. We previously had a very biased cryosphere. So this is from a paper that's just coming out this week by Chris Golaz and others, which I'm a co-author. And you can see that previously had very large biases in sea ice volume that just don't exist anymore in the model. And we are hitting very, very close to trends in sea ice depletion and change in the Arctic. In addition to that, the model now has all the time on cavities in the Antarctic. So these roughly equate to the area of Greenland. So we have flow of the ocean under these ice shelves, and they can be thermally active or inactive. Part of that work has illustrated that we need those ice shelf cavities to be able to reproduce tides, and tides are important for subseasonal out to decadal timescales due to a long period of differences in tides up to about 19, 20 years, depending on how many constituents you would like to include. And you'll note that a big sensitivity of including these ice shelves is in the Labrador Sea. So the Antarctic is directly affecting the Labrador Sea on a day-to-day basis because of the shape of these cavities. Something else we also have finalized in the model now in the beta version for a large ensemble is waves using unstructured meshes, including full wave sea ice interaction and fracture. So this is work mainly done by Erin Thomas, but many people have also pitched in to help get this over the line. And finally, we have a fully coupled Greenland ice sheet with the aim of providing much better fluxes for seasonal periods around Greenland. And we're looking to follow up with this for the Antarctic as well. So we are running a high resolution version of E3SM, but as part of that work, we've encountered a number of problems that have helped inform how we would configure E3SM all the time for high resolution. So what you're looking at here is the high resolution mesh. And there's problems with using a general circulation ocean model for coastal areas. We have minimum depths that are not really appropriate for the Arctic. And so around about 20 meters in this mesh, and we need to improve upon that work. But there's some model physics that are missing, and this is the physics that is missing. We're labeling all this physics as called swift physics, and this is where we are aiming our model development. So embedded sea ice will no longer have in a future version of E3SM a separate sea ice and ocean model. They will be one in the same as just modeling the ocean in two different phases. Surface waves, icebergs, Lagrangian icebergs that are part of the sea ice physics, floating ice shelves because of their influence on tides and tides. And I can go into more detail on this if you have questions on it, but that's the aim of where we're going with this work. There are some critical reasons why we're wanting to embed the sea ice to do with stability for the ice ocean solution with tides added in shallow water. Noting that to represent tides, we need to really model down to only a couple of meters, 5 meters depth as a maximum. We'd like to go to even shallower because that's where so much of the energy dissipation occurs and it really affects the accuracy of a tidal solution. And of course, the feedback from tides is in ice ocean fluxes to the atmosphere. So as we transition, we've very quickly pivoted towards using large ensembles for running E3SM at shorter periods where we're getting around the initialization problem momentarily, but we don't intend to circumvent that forever. And so we're engaged in this blue pulse experiment. The reason it's called pulse is that we need to use wavelets to understand the subseasonal to decadal signals, and an example I'm just about to show. And so we are in the process of spinning up 25 member ensembles for this SORAM configuration. So that stands for Southern Ocean Regionally Refined Model. And we'll be running out to 2050 and analyzing the correlation between thermally active ice shelves in the Antarctic and global sea ice cover. And then also for waves, the impact of wave sea ice and wave atmosphere interaction globally for another 25-member ensemble. We've already completed the large ensemble for E3SM in the top bullet point, and I'm just going to share some results from that. So this is an example of results from one ensemble member out of the 25 showing sea ice extent, sea ice volume, and snow on sea ice volume for the southern hemisphere on the y-axis and the northern hemisphere on the x-axis. So this is a way of presenting the data called lemniscs, and you can see that the color of the trace goes with the date in our model from 1850 to 2050. And as expected, there's a gradual decrease in sea ice volume and extent and snow volume in the model. But we're not really interested in those signals. Instead, we're interested in just the seasonal to annual and up to decadal signals. And this is what happens when these are wavelet filtered. They have to be wavelet filtered because it's a non-stationary signal. And this is these dots here represent the equinox. So this is the ascending equinox, so March equinox on the bottom right, and the descending equinox, the September equinox in the top left. And you can see there are trends in this that cannot be escaped, even though we're interested in just seasonal. And so we can focus in on those trends just for the equinox region. So I'm going to show a graph here that's taking out all of that data. I'm just showing 10 ensemble members. And it produces some unexpected, well, might be counterintuitive results here. So this is showing what we call the interequinoctial range, the range between the two equinoxes of just for the seasonal component. And you might not expect this, but the interequinoctial range is increasing in the Arctic, and it's not increasing in the Southern Ocean at all. As you would expect, the interequinoctial range for sea ice volume and snow volume are decreasing. But the reason this is increasing is that we're losing sea ice in summer faster than we're losing it in winter. And in our large ensemble, this points to an area we're in right now of the least predictability over the last 200 years, the largest ensemble range just in this area for subseasonal to decadal. Actually, this is subseasonal to annual. And so we're in a really hard prediction phase right now in history, just for extent, but not for volume. It's becoming increasingly predictable, as is sea ice volume. So this is the way we're analyzing the data. There's more to come on this. We're employing artificial intelligence in some of the signal processing we're doing, but I'll stop sharing that there and instead just finish off on the targets for AI enhancement that we're looking at in particular. So the aim with AI-enhanced Earth system model development is to solve for physics to the point that we are able with partial differential equations, but then employ AI beneath that level for improved fidelity. So this includes generation of initial conditions using deep learning, things that we would like to relate sea ice freeboard to the internal energetics of the model in ways that don't use traditional data assimilation. And then there's these other examples of full wave emulation. And waves are very expensive to run, but emulation is cheap. Hybrid AI for higher order mixing in the ocean, and deep learning for the friction model used for ridging, which is also really expensive to have a thickness, flow, and macro porous morphology in the model. And finally, we have river deltas nearly working that we'll be looking to use AI to generate bifurcations in the flow of rivers. So in conclusion, this is the world we're going into. We are rapidly pivoting towards AI and S2, S2D. I'll leave the conclusions there for you to read while I take a few questions. Thank you.
Thank you so much, Andrew. That was great. Does anyone have a question for Andrew?
I can ask a quick question. So thanks for excellent talk, Andrew. So you mentioned the difficulties in fully achieving the scale-aware, parameterization or algorithm. So, and then you said, so are you moving away from regional refined grid or into it? Because some of these large ensemble were using regionally refined grid, right?
Yeah. So that's using the regionally refined mesh is using the current version of E3SM,
Okay.
but we're moving away from it in future versions. So that regionally refined mesh has a resolution of 12 kilometers in the Southern Ocean. The new model would be 1 to 10 kilometers globally. So it's a completely different regime. So we've been able to do that using GPUs with rapid speed ups in the code that we don't have in that particular experiment we're running right now.
Thank you.
Just quickly, that I'm not going to be able to say it. The inter-equinox range result. Okay, so the extent has increased, but some of the other metrics decreased. So the predictability might not increase despite that range increasing, right? I mean,
Right. So the predictability part is the spread in the ensemble. And so that
okay, I see.
right,
I see what you're
right.
saying.
So I probably should have highlighted this better and had a better figure for it. But I will point out this was almost entirely generated with AI, this figure. Although
So
I
you blame
checked,
the,
I,
you
I
blame
checked
the
all the
AI for it then.
calculations.
Yeah, there you go.
So this is a very rapid thing to produce. But yeah, so it's this range in the ensembles, and this is the points the reason why we need really large ensembles to get to the predictability question and the
Yeah,
probability. Yeah.
yeah,
Does that make sense?
yeah. That makes more sense. Thank you.
Okay.
Okay, any other questions? If not, maybe we'll move to Alec.
Sure.
Alec Petty is a research scientist at the Earth System Science Interdisciplinary Center at the University of Maryland. He's a polar climate scientist exploring the causes and consequences of sea ice change using climate models, remote sensing, and machine learning. Thank you, Alec, for being here.
Great. Thank you. Can you hear me okay and see the slides okay?
Yes.
Fantastic. Yeah, so going to be talking today about efforts to constrain CMIP6, but really any model's sea ice output with data collected by NASA's ISAT-2 mission. Shout out to the colleagues on this project, Chris Cardinale, he's a postdoc of mine at ESSEC as well, and also Maddie Smith, who's on the call, based at Hui. And so this is primarily work that we've undertaken, funded by the ISAT-2 science team. It's a 3-year project. We're just approaching the end of that, but we do have some other funded efforts that I'll mention along the way too. A lot of the results that I'll be talking about today are part of this paper that came out in GMD last year. So if you do want more details about the things I'll be talking about, do check that out, and I'll leave that link up on the final slide too. Yeah, and also shout out to Andrew, because some of the things that we'll be talking about today are definitely ideas that he kind of pioneered and talked about in some of the early adopter phases of ISAT2. So thanks to Andrew. I am motivated by plots like this. So this is these are plots of September Arctic sea ice area on the left and volume on the right, and I'm sure a lot of you have seen plots like this before. But yeah, I like showing them just because they really introduce the different types of uncertainty that we're dealing with when we're trying to use sea ice models to understand sea ice variability and future projections. They show the pretty wide intermodal spread represented by the shading, but also some of the big outliers we see in the dots too. There's the internal variability of the climate system, represented by some of the wiggles and some of the longer multi-decadal sources of variability. And then projecting forward in time, we have scenario uncertainty too, represented by the different colors. So lots of sources of uncertainty, and we have to be very careful about how we use these large model suites to do science, but there's a lot we can do if we get that right. There's been lots of efforts in recent years to develop some pretty sophisticated calibration techniques to improve predictions of target metrics like an ice-free Arctic. But I think maybe there's been a bit more kind of open debate and confusion potentially about the types of observations we should be using to do that type of work. And that's where we're hoping to provide a bit more input on. But it's not just these kind of long-term multi-decadal projections that people are using CMIP6 data for. They're also increasingly being used as key training data inputs to simple and also very sophisticated machine learning forecast systems. So there was a big splashy paper that came out in 2021 doing this with deep learning, and there's been a few others since. So I've seen papers ranging from kind of nowcasting through to seasonal, through to interannual timescales, and CMIP6 CIS outputs continue to be a key input data sets to all of these systems. So again, thinking about how to use that data is a key question. The observational data that people tend to look at when evaluating CMIP6 data, except for Andrew, is the passive microwave record of sea ice concentration and sea ice area. There's a good reason for that. It's a nice 40+ year time series. We're showing a record of sea ice area for the Arctic here from the OCSAF product in black, overlaid on CMIP6 outputs of sea ice area. And yeah, it's a fantastic data set. It's quasi-daily, virtually uninterrupted, and it captures some of the big trends and interannual variability signals of Arctic sea ice. An example is shown on the right, but the big downside of the concentration area data sets is that it doesn't give us a huge amount of information within the ice pack, especially in winter. And we know there are big thickness gradients present in the Arctic and in the Southern Ocean, and that's the type of information we want to try and bring into these observational assessments. Obviously, the big downside, as we highlight in this panel, is some of these new emissions like ISAT2, that the time period is just way less compared to that longer 40-year record. So we need to be extremely careful about how we use it when we want to do climate scale assessments and potential calibrations. So yeah, why should we assess models with ISAT2 data? ISAT2 is an amazing mission. I've been working on it since just prior to its launch in 2018. It's a highly accurate laser altimeter that gives us these very accurate measurements of height. And over sea ice, we get measurements of height over the ice surface and also within these open water leads. And from that, we can produce observational measurements of total freeboard in this case. So the extension of sea ice and its overlying snow cover above a local sea level. Those freeboard measurements are historically achieved to estimate sea ice thickness, and we use this kind of hydrostatic equilibrium assumption where we feed in freeboard together with some ancillary information such as snow depth and density and ice density to convert that to thickness. When we make that conversion, that's when we start introducing a lot of uncertainty. So it's the uncertainty in those input assumptions which really drive the uncertainty in our derived estimates of sea ice thickness. So we're interested in kind of two things. Can we use the estimates of sea ice thickness from ISAT2 to evaluate models? And can we use the more primary observations of total freeboard to evaluate models as well? Models, in contrast, simulate the ice thickness distribution, but are increasingly outputting estimates of ice freeboard to enable such comparisons. So doing this work is very timely. So again, thanks to the people that have kind of encouraged this type of work across the various modeling groups. As I said before, there's a bunch of other cons associated with this type of analysis. The very short time period, so internal variability is going to be very high and needs to be considered. ISAT2 isn't perfect. There's still plenty of issues that we need to think about. There's some coverage issues at the margins, wave contamination of our height and freeboard signal. We try and filter that out, but that obviously reduces coverage in these very important marginal ice regimes. And then there's some quite unconstrained uncertainties, which is always a problem for some of these sea ice observational data sets, primarily driven by the fact it's very hard to obtain basin scale independent truth data to compare these and remote sensing estimates too. So that's just like ongoing work that we always need to consider. So this is what that data looks like. These are the maps showing averages across a 7-year period, I think, 2018 to 2024. We've got the Arctic on the left. That's going to be the prime focus today, considering the audience, but we've got some Southern Ocean results on the right too. And then the lower panels are showing the passive microwave sea ice concentration data. We've got the annual means and then the kind of winter max in March and then September, the minimum for the Arctic, obviously flipped for the Southern Ocean. And then we've got total freeboard, that more direct measurement at the top. And then for the Arctic, we have the estimates of sea ice thickness. We're a little bit less confident about snow loading and that conversion from freeboard to thickness for the Southern Ocean, so we don't include that in our analysis. But that's something we're always thinking about. Yeah, the key is, again, if you look at thickness, we see much more information popping out. So we see these strong gradients in thickness across the Arctic Ocean. But interestingly, again, if you look at the maps of freeboard, we also see pretty similar gradients. So maybe, as a first order proxy, freeboard is giving us more information, especially compared to the winter concentration maps. Similar story for the Southern Ocean. Yeah, there's a lot of details about how you might want to do these observation to model comparisons, especially when you start wanting to think about freeboard and the conversion between thickness and freeboard and how that's represented in remote sensing versus the model world. As I said, a bunch of CMIP6 models now do provide direct ice freeboard output that they calculate either online or during some post-processing step. It's essentially a combination of the ice thickness and the densities to make that conversion. You need to add on the snow thickness to obviously compare it with the total freeboard that we measure with ISAT2. This is all pretty much new work. We hadn't really seen anyone that had assessed these new freeboard outputs in CMIP6, so we did a little bit of work on trying to kind of sanity check them, and we definitely found some models that are producing some pretty spurious results, and maybe some mistakes were made in the conversion and the densities that they were assuming. Yeah, the different model results are shown on the right there. So there's yeah, some variability. Some of that variability makes sense and some of it doesn't. So a simpler approach that we take for the following slides is we actually just prescribe a sea ice bulk density, and we use the same pure ice bulk density that we use in our remote sensing methods. And we can then apply that to all of the CMIP6 archive and produce a kind of remote sensing-like total freeboard estimate to compare with ISAT2. Thanks to Dave Bailey, who I think I saw on the call, who helped us understand a lot of this in more detail too. When we want to do these observation model comparisons, we need to think about this idea of plausibility. We are just one realization, and these climate models represent multiple potential realizations. And internal variability is what drives that potential spread across the models. So we try and calculate and understand this internal variability across our different metrics and time periods. It's a notoriously hard thing to try and estimate. All the models give you quite different answers, which is a challenge. And not all of these models give us very large ensembles to more robustly calculate that, but we do our best, and we come up with this CMIP6 model mean internal variability estimate for the different metrics we're interested in, which is shown by the right column. And then we also need to think about observational uncertainty. So this is, again, notoriously hard to do, and various studies struggle with this. We took the approach of trying to kind of summarize some of the estimates from the literature. We're doing, some of these, especially sea ice area, tend to be estimated through a kind of interproduct spread, whereas for remote sensing altimetry basin scale measurements, we tend to look at comparisons with independent data. So this was our kind of summary of those various efforts, and we come up with a low and a high observational estimate that we apply to our basin scale means. We could put that together into this plausible range calculation, which is a combination of those two factors. So again, the models aren't supposed to agree perfectly with the observation, but we hope that they match within some kind of prescribed range at some confidence interval, the 95th percentile in this case. So we produce plots then that look like this for our various metrics. So this is showing a plausibility assessment of Arctic Ocean annual mean total freeboard across this 7-year period. The observations, ATL20 in this case from ISAT2, are shown by that red line and the circle at the top. And then we have the CMIP6 intermodal mean in black. The lines, the horizontal lines, represent that plausible range. Again, it's a short time period, so internal variability is high. That makes these assessments difficult, but there's a lot we can still do considering that large range. So we can see that in this case, the majority of models are considered plausible, but there are still several models at the lower rankings here that we can potentially discard as implausible based on this assessment. But a good performance from the CMIP6 multi-model mean overall, which is cool to see. Things are a bit worse for the Southern Ocean. We see a much more significant bias between the CMIP6 intermodal mean and the ISAT2 data, and the majority of models are considered implausible compared to plausible in this case. The panels on the right are showing the mean absolute error. So here's where we try and look more regionally. So we compare the model and the observation at the grid scale. The fact this doesn't increase monotonically compared to the data on the left is due to competing biases, right? So we have regionally competing biases, which maybe is making some of these models look better than they actually are doing. And I'll talk about that in a few slides' time. We then try and bring this all together into some coherent plausibility matrix, we call it, where we have our various metrics in the two hemispheres represented in columns and the different models below that. We have the CMIP6 multi-model mean at the top row, then all the individual models below that. These are ranked, but again, we shouldn't really consider them as kind of, we shouldn't pay too close attention to the rankings. What we should really think about more is plausible versus implausible, and those implausible metrics are shown by the solid bold boxes. And so there's a lot to see here. There's more implausible metrics for the Southern Ocean versus the Arctic. Maybe some of the models are struggling a little bit with the freeboard and thickness in summer compared to winter. Maybe more negative biases compared to positive, but it depends what you're looking at. And then, yeah, our work so far has really been thinking much more about how to use ISAT2 data to do these kind of assessments and how to consider internal variability and observational uncertainty. But we did want to highlight some potential impacts of doing these constraints. So here's the plot I showed earlier showing the CMIP6 data versus observations. On the left, we have, that sea ice area projection, the raw CMIP6 data in gray and black, and then CMIP6 constrained just by the sea ice area plausibility analysis in red. We can see that causes a slight change earlier in the record, but if you care about things like an ice-free Arctic, it actually doesn't really change the data at all. But when we start bringing in constraints of sea ice thickness and freeboard from ISAT2, we see a much bigger shift and an earlier ice-free Arctic projection just based on that additional constraint. And we see more significant reduction in model spread too. As I said, we've also undertaken a bunch of regional sea ice assessments. So this is where things can look a little bit more problematic for some of the models. So even those models that perform extremely well at basin scale means have regions that they're still struggling with. We see a lot of those high-performing models struggle to capture the thicker ice north of Greenland and the Canadian Arctic archipelago, represented by those red and hatched regions. So a region that's notoriously challenging for models to simulate still. But yeah, there's a lot more regional assessments and composites we include in the paper if you're interested. And another point is this is all just with freeboard. So again, highlighting that the freeboard data itself can give us some interesting regional information and assessment. Just a couple slides on our more recent work. So that work was all published last year, but we're trying to keep this somewhat live and updated. So here Chris has done some really nice work on bringing in new models and also extending the observational record another year and seeing how that influences our plausibility results. One of the models that we introduced was the CSM2 less melt output, which was a nice effort by the CSM2 folks to make a few key parameter tweaks to improve the representation of sea ice. And they think that improved their sea ice performance, and our analysis really confirmed that. It's the top performing model relative to all the CMIP6 model outputs. And then on the right, we're showing the plausibility change from our initial results to this extension of some new models and an extra year of data. And we see some interesting shifts. So trying to think about how we can keep this kind of going, and other models, E3SM and others that we could start introducing into this framework too. Yeah, I'm also pretty invested in trying to continually improve the remote sensing observations that we're using to do these kind of assessments. This is some work I'm very excited by that I'm working on very actively right now. As I said, ISAT2 has some issues. It's not perfect. We have issues at the ice edge. We have data dropout due to clouds. So what we're trying to do here is I'm trying to bring in some additional satellite remote sensing data to improve our estimates of basin scale sea ice thickness and volume. Here we're bringing in thin ice thickness from SMOS and SMAP around the ice edge to improve those gradients in thickness as we move through the marginal ice zone. And we're fusing that all together in this nice machine learning Gaussian process regression package called GPSat, which is now giving us results that look like on the left, complete basin scale coverage every day, which I think is going to make that kind of model assessment work even easier. And then finally, there's some work that our group is doing right now to look at melt pond representation in CMIP6 models as well. This is work being supported by the Cryospheric Sciences program, and we're interested in seasonal melt feedbacks and how models simulate that. So our kind of first step of this project was really just to see how the models capture the seasonal and regional evolution of melt ponds across the Arctic. And luckily, there's been some new observational data sets that are enabling this kind of basin scale comparison. So Maddie's working hard to write that up right now. And yeah, we presented some of this work at the CSM meeting a few weeks ago and Ocean Sciences last week. So I think we'll share a link to the poster in the chat if people are interested in melt representation too. And yeah, I think that's it. Just some final thoughts. Yeah, interested in how we kind of keep this type of assessment moving forward. We've been thinking a lot about CMIP7 prep, but things there are a little bit delayed. So we're also thinking about how we can just maybe make this flexible to new model results as they come in and be a little bit less dependent on these CMIP model phases. We're interested in thinking about how we can share these updated plausibility assessments. Interested in better constraining internal variability. Very excited by what Andrew said about emulation and large ensembles, which I think could be really, really helpful. And we're interested in working with the community to use these assessment frameworks together with their fancy recalibration methods to improve predictions. And I'm a part of the CICE model intercomparison project, and there's some really nice discussions going on about how we can work together on that too. So I'll leave it there. Thank you.
Thank you so much, Alec. That was fantastic. Any questions for Alec? Muyen, go right ahead.
Yes, thanks, Alex. I don't have a question because you did show the performance of different models for the CIs,
Yeah.
My question for you is, as far as I know, a lot of other CMIP6 models also use the same CIS model in the system. So why only the CESM perform better than the others, since they're using the same CICE?
Yeah, I mean, I think it's always this debate between CIS physics versus forcing, right? And
Right.
there's kind of different camps, some people that think we overestimate physics and others think, and we should just get the forcing right, whereas others think the physics can really, really help improve things. So, I mean, I think it depends again on the question and what you care about. It's definitely come up with our melt pond work because for the 6 models that produce melt pond outputs, they all use CICE. But there's some slight differences in the physics they use within CICE and the different melt pond schemes, and that does produce very distinctly different seasonal melt pond distributions. So again, I think if you go to kind of smaller or more focused metrics, the physics really starts to show up. But yeah, if maybe you care about longer term decadal scale projections, maybe the physics can be a little bit less meaningful. But yeah, I'd say it's a pretty active debate.
And one thing I was curious if you kind of regroup your evaluation just based on the CIS models, what they use. That work tells more about, what's going on with the ice model itself and what's the coupling with the other component. And in terms of your last call about the large ensembles, I guess one thing I want to say is, yes, that really helps a lot understanding the physics, natural variability or the internal variability. But in terms of the international, as we can see, even in the CMIP6 compared to CMIP3, the model has increased from like 20 to 100, but
we do not really improve our understanding or the projection of the sea ice free a lot. So that I think we got to be cautious on that one because what I saw I really like to see your result. You're adding the observation and constraint, increase the model projection, and that's consistent with our 2009 paper and also the timeline. When we use only 23, subgroup of 23 get 7 models, we also get about 2040, 2050. So this is consistent in the model in the 3 phases. So that's really encouraging to see. But I really like, I'm glad you showed this paper. I really like to see when you regroup them into different ice models, that's maybe we can understand more on them. Thank you.
Yeah. Yeah, no, I appreciate the thoughts. Thanks. Yeah, we haven't attempted that grouping. And that always kind of comes up in papers that, at some point we need to think about better ways to weight models based on the similarity of their underlying model components and things like that. But yeah, I've not seen a simple way to implement that, but that'd be good to think about.
Oh, just one more question. So you're looking ice area, not sea ice extent.
Mostly we do area, yeah. Yeah.
Okay. Thank you.
So I saw the next hand I saw was Morteza.
Yes. Hi, this is Morteza, and I'm sorry, I'll keep my camera off. I'm on the move. Fabulous talk, great work, and I must apologize in advance that the question may not exactly be directly related to your talk.
That's okay.
It's mostly out of ignorance, but I found it very interesting to look at these models and whether the confidence interval is capturing the observation. My question was related to sort of what you mentioned about the unbounded uncertainty of ISAT2 and what that means. Particularly what I've been thinking about is given how narrow the ISAT2 tracks are, and then we aggregate these over time, there's obvious uncertainties introduced that I don't believe we can perhaps fully characterize in terms of what's happened in the meanwhile, how's drift or ice dynamics affected that. And I feel like there is no better person to answer that question. That's me posing it to you in an unrelated talk. What are your thoughts on that? Have there been studies like what would the world look like if ISAT2 had full spatial coverage, and how far are we from that essentially?
Yeah, I guess maybe there's a few threads there. One is I think maybe you're getting at this idea of like, can we kind of propagate uncertainties through in, kind of expected sources of uncertainty in our thickness or our freeboard retrievals and use that to come up with basin scale uncertainties. And I think I've kind of gone off that method because I think there's a lot of issues with sampling and representation that are hard to really understand. So yeah, I've tended to steer more into the just assessments against independent data and using that to kind of guide what our errors are, rather than the kind of more theoretical observational uncertainties, which I think can be often quite wrong.
Right.
So, and yeah, there is a paper that just got published on the cryosphere recently in the discussions during a kind of sea ice thickness intercomparison thing. And I think that talks a little bit about the different ways that uncertainty is calculated with these remote sensing products. And I think that has some decent discussion in it that might be helpful and relevant. Sorry, a bit of a hand wavy response, but
no, it makes perfect sense. I didn't expect much more of a
surprisingly
quantification. Yeah. Well, and thank you for pointing out the paper. I hadn't seen it. I'll look for it.
Cool, appreciate it. Thanks.
The next hand I saw Dave Bailey.
Yeah. So Alec, you and I have talked a lot about this too. I mean, there's a lot of assumption that goes into that sort of hydrostatic computation of freeboard and the densities you're using and things like that. So I think one of the other interesting things to look at is like, well, the models that had prognostic salt in them and and are you taking into account the density of the brine when you're doing the calculation and things like that. So so there's one thing I've been sort of more careful about with implementing this freeboard into the CSM3, for example. And then, and then the other concern I think I mentioned before too is, occasionally we get like very small negative values from that equation too. And
Yeah.
you know, so I worry about some of that too.
Yeah. 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 And we talked a little bit about this, but yeah, for the others, it's, you know, in the observation, there can be these weird things that we do in our processing chains, like we might set negative freeboards to 0. Um, that can create biases. You know, some of those kind of edge cases that we maybe don't think too much about. When you start doing these comparisons and you're trying to kind of really do these properly, you need to kind of maybe revisit some of those ideas. So yeah, I think at the very least that was part of our goal too, was just to kind of trigger some conversations about things we might want to think about when we start assessing things in more detail. But yeah, thanks to you, Dave, for helping us understand all this. So, um, yeah, hopefully we'll get there.
I see another hand up, Marika.
Hi, Alec. Really nice talk. And I think these new diagnostics are great. I mean, I think it's really valuable work. I think it would be really helpful to think about how to use them in the model development process.
Right.
And it seems to me like there's some fundamental challenges there with a
Yeah.
need for large ensembles, the fact that we do a lot of our development in a pre-industrial climate state.
Right.
But maybe there's some creative ways we could get around some of those challenges, because I think they would just be so helpful, you know, and we've talked a bit about this in the context of the CESM3 and developing that model. But if they were almost used regularly in, you know, the whole model development process, I think that would just be
Yeah.
fabulous to figure out how to make use of this great work for that.
Yeah. Yeah, I mean, an example of that is, yeah, I mean, like Andrew's talk, he's using ISAT data, and I think I've realized in our conversations, ISAT data would have probably been more useful, considering people running this with historical forcings. And, you know, we jump to the latest and greatest, but that isn't always necessarily what 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 you guys need. So definitely trying to think about how to revisit the ISAT data. I think some of the reanalyses that are starting to come out, I think, are going to be helpful too. I think there's been some nice progress of people thinking about longer term reanalyses and, you know, improvements over biomass and yeah, things that can be, you know, not perfect on a given day, but good for kind of climate scale evaluation.
Yeah.
I'm interested in some more data-driven approaches to kind of reanalysis generation too, and other proxies we can use to try and come up with some ballpark thickness estimates over longer time periods.
Yeah. And I think what you've done in assessing the models after, you know, these kind of finalized models is really useful in its own right. So I'm not at all saying that, you know, should
Oh
stop.
yeah. Yeah.
But it also, I just think that there would be a lot of value in figuring out
Right.
how to better do this when we're actually developing our
Right.
models too.
Well, and Andrew's kind of doing that in seemingly this very nice, sophisticated way of, you know, having the satellite baked into the models and simulating freeboard along the tracks, and that's cool. But yeah, there's maybe some middle ground for people that don't want to do that or don't have the resources to do that, where you want something a little bit easier, but useful for development evaluation.
We have time for a final question.
Well, maybe a quick question
Can-
to Andrew about that. If,
Yeah.
you know, are they at E3SM, is that how much is the ISAT evaluations guiding development, or are there other ways that he's kind of evaluating thickness?
How is it guiding development? It's telling us a lot about how limited our model is in some ways.
Right.
I have to, I'm afraid I'm a blatantly honest modeler. And so, yeah, it's telling us quite a bit about things that we need to improve, most of which is associated with processes we just don't have and resolution we don't yet have.
Right.
So, you know, we still live in fear that some of the AI approaches using altimetric data will also just still result in having a very nice initial state that very quickly degrades in the model because it's just not close to the coupled state of our simulations. So that's a non-answer really for your question.
Yeah.
And there was one comment in the chat. I know we're like a minute to the top of the hour from Yunju on, I guess it was directed to you, Alec, on any comments on the size of ensemble members with model skill evaluation.
Oh, yeah, I don't know. I feel like we've not got a great answer for this. And we thought a bit about it and we pick arbitrary thresholds of like 10 members is good. I feel like at the CSM meeting, everyone always encourages like 20 or 30 members. And everyone seems to have their favorite idea of how many members are good for capturing internal variability, the thing we're interested in. Yeah, I think I defer to the modelers who know more about that than me. Yeah, Dave said less melt was only 5. So it's something. Something's better than nothing. Oh, Andrew's got his hand up. Maybe he's got some thoughts.
I just realized in response to that question and also your question, something I should have pointed out, and actually was the point of the figure I had in my talk, is that one thing that comparison with ISAT and ISAT2 is showing is that on the whole, our freeboard average is within an acceptable range, but where we're really missing is the underlying heterogeneity of the pack that's just not represented in models. And that's having a big impact on the large scale evolution of sea ice. So that's what your work is pointing to, and other people who work in altimetric data is that's the key model improvement is heterogeneity.
Right. But yeah, I mean, and just response to Dave's less melt was only 5. I mean, maybe the nice thing there is like less melt just agrees with the observations so well. But yeah, if there were bigger biases, there would have been this kind of open question of like, is that because of the limited ensemble size? A little bit more so, right? Yeah, I don't know.
We don't bias correct our coupled runs, but
No, I'm just saying less melt was so good, so a lot of the ensemble members perform really well. But if there was bigger biases, then there might have been this open question of like, oh, should we have run more members? And maybe some of those might have performed closer to the obs.
sure. Well, I mean, in a sense, the less melt was sort of extra ensemble members beyond the CSM2 large ensemble. So, but no, I was responding to Jia Wang's question about, do we do bias correction? And certainly if we're doing predictability runs, we do, but for most of our fully coupled runs, we do not.
Andrew, good question.
Well, we've reached time, Tony. I don't know if we have time to allow anything else or.
Yeah, I mean, I can stay on and keep the line open if folks are still available, but Andrew and Alec also want to be respectful of both of your schedules. I know we have taken the full hour.
Okay, I think we're good. Thanks so much, Andrew and Alec. We really appreciate the time you put in on these presentations. Thank you to everyone who showed up today. I think this was a really great session. So thanks, everybody.
Thanks, guys. Really appreciate it.
Thank you all.
Bye.